We rely on the physical universe following predictable rules. Matter occupies space. Light travels in straight lines. But when a star, massive enough, runs out of fuel, it collapses entirely into a void that traps light, breaking the standard laws of physics. The perimeter of this void is the event horizon. It marks a strict mathematical boundary. Once an object crosses this line, the velocity required to escape the gravitational pull exceeds the speed of light. Because nothing travels faster than light, nothing can return. This extreme density is the byproduct of a dying star. For millions of years, the outward pressure of nuclear fusion balances the inward crush of gravity. When the nuclear fuel is finally exhausted, gravity wins, crushing the star's core inward until it compresses into a point of near infinite density. For decades, these collapsed stars were considered mathematical oddities. It took the work of physicists like John Wheeler, who officially coined the term black hole in the late 1960s, to help the scientific community conceptualize them as real physical objects. The death of these massive stars proves gravity's ultimate strength. Given enough mass, gravity wins by subtraction, physically deleting matter from the observable universe. Black holes exist on vastly different scales. Theoretical models suggest microscopic primordial black holes, the size of an atom formed moments after the Big Bang. Conversely, the stellar mass remnants found throughout our galaxy often hold the mass of 10 suns, packed into a sphere the size of a city. Scaling up further requires massive collaborative technology. Using Earth-based arrays like ALMA, astronomers peer into the centers of galaxies to locate supermassive black holes. The Milky Way revolves around Sagittarius A star, an object containing the mass of over 4 million suns. In 2025, researchers identified the oldest supermassive black hole ever observed. Existing just 500 million years after the Big Bang, the object was detected actively devouring a star, proving these entities have been growing since the universe's infancy. Some of these giants do not stay anchored. Astronomers have observed runaway supermassive black holes that have been ejected from their host galaxies. These objects tear through open space, pushing a bow shock of gas and leaving a 200,000 light-year-long trail of newly birthed stars in their wake. These objects dictate the life cycle and structural movement of the galaxies they inhabit, acting as primary drivers of cosmic structure. Approaching the event horizon reveals a ring of superheated gas. This is the accretion disk. As matter gets pulled toward the void, friction superheats the gas to millions of degrees, causing it to emit intense radiation. Immense gravity warps space-time, bending light from behind the disk over the top, creating a folded illusion. Closer in, the photon sphere traps light in circular orbits. Meanwhile, Doppler beaming compresses approaching gas, making it brighter and bluer, while receding gas appears dimmer and redder. Beyond the disk, tangled magnetic fields in a billion-degree corona can violently redirect incoming material. This creates particle jets that blast away from the poles at near the speed of light, extending for hundreds of thousands of light years. These objects are revealed only by the extreme radiation emitted by the matter they consume. Entering the immediate gravitational field of a stellar mass black hole is fatal. The gravity gradient changes so rapidly over short distances that the pull on your feet would vastly exceed the pull on your head, stretching matter until it snaps in a process called spaghettification. Paradoxically, a supermassive black hole offers a smoother entry. Because its event horizon has such a massive radius, the difference in gravity between a person's head and feet is negligible at the boundary, allowing a physical body to cross the threshold intact. But the space around a rotating black hole, described by the Kerr metric, presents a different physical reality. The black hole spins with perfect rigidity, physically dragging the fabric of spacetime along with it, like water circling a drain. This equation from the Kerr metric calculates extreme time dilation inside dragging spacetime. A clock orbiting near the horizon slows drastically compared to one in deep space. To achieve immense dilation, 1 hour equaling 7 years, the black hole's angular momentum must approach the speed of light. Slipping into the gravity well of a spinning black hole means accelerating your timeline relative to the rest of the universe. It functions as a rapid, one-way time machine into the distant future. Once past the event horizon, the trajectory inevitably points inward. However, the mathematics of a spinning black hole describe a bridge connecting to another region of space-time. As early as 1935, Albert Einstein and Nathan Rosen calculated the mathematical shape of this theoretical structure. Today, we call the resulting paraboloid-shaped throat an Einstein-Rosen bridge, or a wormhole. This scientific excerpt outlines the physical caveat. Astrophysical calculations show that naturally forming wormholes are inherently unstable. They would gravitationally collapse and pinch off the moment they formed, destroying anything inside. In 1988, physicist Kip Thorne and his students proposed a theoretical workaround. By lacing the throat of the wormhole with exotic negative energy, a repulsive tension could be applied to counter the gravitational crush, propping the tunnel open. Harnessing that energy requires the Casimir effect, an artifact of quantum mechanics. Surviving the interior of a black hole requires bridging the physics of the astronomically massive with the subatomic. Every path inside a non-rotating black hole ends at the singularity. Here, the star's entire mass is crushed into an infinitesimally small, infinitely dense point. The singularity creates a hard limit for science. At this exact point, the smooth curves of general relativity collide with the jagged rules of quantum mechanics. The mathematics yield infinities, and the current laws of physics fail. Describing this violent collision drove the careers of physicists like Stephen Hawking. They dedicated their lives to analyzing the boundary conditions of black holes, searching for the missing math that unites gravity with the quantum realm. The singularity marks the physical boundary where existing theories fail, leaving an incomplete map of how the universe operates. It remains a gap in our knowledge, waiting for a unified theory of everything to provide a more complete description of gravity.